so I don't know why I had any hope that this was going to work. It just totally doesn't. Meh. This is a Hall effect sensor. Now, you use this for sensing magnetic fields, proximity detection, position detection, all kinds of things. Now, they've come a long way since the early days. I mean, this is a tiny little thing, but once upon a time, current was unknown. Magnetic forces on current were weird and mysterious. Well, today, we're going to go back in the history and we're going to figure out how this guy works. We're going to talk about Hall effect and the Lorentz Force, because really, that's what we're talking about. So, just to get it out of the way right off the top, we're going to talk in detail about this, but just to cut to the chase and, you know, big spoiler, Hall effect, what it is, let's say that you've got a conductor. How am I going to draw this? Okay, so let's, no geometry, Pete. Whoa, wow. Okay, you might want to cut some of that, or you might not want to. So let's say you've got a conductor, and like a bar, okay. And I've got, you know, a wire attached here, and this is my negative source. I've got a wire attached to the back out here, and this is my positive source. So I've got an electric field going this way. Well, what if you brought a magnetic field into proximity? Now, specifically, you've got like force lines going this way, right? And so what'll happen is, and this is, if I remember correctly, this is a north pole, so lines are coming out of the north pole. So underneath, you've got the force across the conductor. What'll happen is that you will get negative charges that migrate over to your side. And then you get positive charges on the other, and I think, you know, holes that go that way, so it's probably something like that. And so the upshot of this is you can actually sense a voltage on these 2 points that indicate when a magnetic field is present, okay? If there is no magnetic field, the current is just going down and the charge is the same on either side. But when the magnetic field is there, you get this separation of charge on either side of the conductor, and you get a voltage, and they call it the Hall voltage. And that, in essence, is what the Hall effect is, and it's pretty snazzy, huh? Edwin Hall was the discoverer of the Hall effect in 1879, and he wrote it up in a document called On a New Action of the Magnet on Electric Currents. And he wrote this in pursuit of his doctoral thesis at Johns Hopkins University in 1879. Now, the way he set this up, and we're going to go into it in more detail in a bit, because it's really a hoot to be able to read this. He set it up basically like I showed you, except it wasn't a huge bar that looked more like a ramp. It was more small. Bunsen cell, one Bunsen cell, right? If you go back in the history, that is a 1.9 volt carbon zinc cell, so it sounds like a dry cell. 2 centimeter by 9 centimeter gold leaf that he measured at 2 ohms, and a Thomson galvanometer to read, right? So all the elements that I had, just a little bit different. This guy, do you know what that is? This is a crazy thing. Check it out. If you if you look this up, you'll see pictures of these things, like a box that's on a tripod that's got a couple of wires coming out of it, and mounted to it is like a mirror. And the way this thing worked, right, is they would pass a current through this, and there's a big inductor in there, and it would turn, right? And the mirror, they would have a beam of light pointed at the mirror, and then you know, when there was a current, it would actually turn. And so you've got the screen. You've got the screen behind it, right? And so when this turns even slightly, you can see the beam move, and that's a Thomson galvanometer. History, man. So Edwin Hall, this is where it came from. Now, why does it actually work? What was he seeing? We're going to go into detail on that, and it's called the Lorentz Force. So, what was going on? Well, remember that they didn't really know what electrical current was yet. They were still poking and prodding at electricity to see how it worked and what it did and all this stuff. I love stuff like this, right? It's all the things that the physical principles that sort of show you what's at work behind the scenes, right? The man behind the curtain. I love stuff like this. But the reason it worked, right? Edwin Hall, he got a positive result from what he was trying to do. What he was trying to do, right? He was trying to affect the path of the current through the conductor by literally attracting it with a magnetic force. And he got a positive result, but not quite for the reasons that he thought. A couple years later, Lorentz Force. Hendrik Lorentz, hopefully I'm pronouncing that. Lorentz, I don't know. But in 1895, he wrote this up. He gets credit for the derivation. But he was building on the earlier work of Oliver Heaviside from 1889 and James Clerk Maxwell from 1865. So on the shoulders of giants, right? What a magical time this was. Bell was doing his stuff, and oh man, that would have been awesome. Now, what Lorentz Force actually says, what the equation says, and this looks very benign for what it actually is, that the force on a moving charge is equal to the electrical field applied to it plus the cross product of its velocity, the charge's velocity, and the magnetic field that's applied, okay? Now that looks, what does that mean? Okay, well, first thing I'm gonna tell you is everything in here that's not a Q is a vector, right? So there's 3 dimensions. A vector is magnitude and direction, right, in case you're not a math person. But what this is basically exactly what I showed you in the experiment before, right? So if I've got, right, if we're just working in 2 dimensions here, and I've got a charge that's moving this way with an applied electric field, right? So we've got negative down here and positive down here. And I've got a B field, and right, this is the tip of the arrow, so you're looking at the arrow coming up. Negative charges are going to tend to go that way. Because the force on them is going to act that way. And positive charges, right, so negative ones will go that way, and positive charges will go the other way. Oh, crazy! So that's effectively what Lorentz Force says in its simplest form. Now, brief aside, this is sort of like right-hand rule. Oh my gosh, go Google image search for right-hand rule because it's astonishing. It's safe for work, trust me. You're not gonna get in trouble, I think, but you're gonna see some of the most whacked out. The way I read this is, my thumb is the B field, my forefinger, index finger is the applied electric field, and my middle finger is the force. Do with that what you will. Lorentz Force. Since we've been given the write-up of Hall's, I really want to try to replicate this. Can we replicate this and actually see the Hall effect in its natural state? Well, I put a few of the numbers, right, and I will post a link to the document. You must go read this document. It's short, it's amusing, it's history, and you should know it. But I posted the first bit of his experiment chart just to look at the units to examine, can we replicate this? Well, okay, the first thing I'm looking at is the magnetic field. And the first number he's got is 11,420 H. Well, okay, what's H? Well, H is defined in the document as 0.19, I don't know what. Now, you do a little bit of research and it's the same magnitude, order of magnitude as a Gauss, so that might be his Gauss measurement, maybe. The units here are CGS, so we're going to talk about that. That's a whole thing. Not too in-depth, but enough for me to go, CGS units. But just to get a rough idea of the playing field here, okay, 11,420 times 0.19 Gauss. Well, if you do the math, and we always need to reset your Gauss versus Tesla thing. I always have to do this. 1 Tesla equals 10,000 Gauss. The Earth's magnetic field is 50-ish microteslas, around half a Gauss, I'm sure, depending on where you're taking the measurement, so around the same order of magnitude. And neodymium magnets generally can get into single Teslas, so that puts us in the ballpark for a field strength that ought to be able to do this. Now the other numbers, those are a little trickier. Okay, so looking at some of the other numbers, a couple of things, all right. One point, sorry about mixing the markers. We were trying different colors to see what worked best, and we had this red one that was really nice, but when I went to erase this, it looked like we murdered a nerd and spread it all over the whiteboard. So that took us a while to clean up, and we're not using the red anymore. The other thing is, in the previous shot, this number was 0.016, which was a mistake. I corrected that. Now, let's talk about the numbers. Now, these are CGS units, not SI units, okay? And in short, CGS is, if I remember correctly, centimeter gram second. So everything they're trying to figure out in nature is derived from those 3 units, sorta, kinda. And their units for current, 0.16. Well, okay, what we know is the Bunsen cell is 1.9 volts, and he claimed, he stated that the gold leaf presented 2 ohms of resistance. So we're talking about almost an amp worth of current, right? Well, that's not an amp. Well, when you dig into what the units of the day were, the CGS units, what you come up with is a biot. And that's a French name, so it's something that's not biot that's pronounced. Or the AB ampere, AB ampere. And if you're thinking of AB normal, you're not alone. But when you read about it, what you find is the biot, or AB ampere, is equal to 10 amps. And the way this was measured was 2 parallel wires of a certain length and a certain amount of current that created a certain amount of force between the 2 wires, and that's what they called a biot, or an AB ampere. And that's how they measured current, right? They still didn't know what it was. So if you do this, this becomes, it moves an order of magnitude, and that's, half an amp. Okay, we're in the right order of magnitude, right? And it was a battery. Your standard dry cell can't be expected to last very long, so okay, we're in the right ballpark. Now, you apply the same thing to what he lists as the current through the galvanometer, the Thomson galvanometer. And you divide by 10, and what that's going to be is 232 nanoamps. So very small current through the Thomson galvanometer. Now, if you do the rest of the math, if I'm looking at this with a scope, which has got 10 milliohm, that should be a big M, megohm. So if I've got did I do something? Okay. So you do back out 232 picoamps into 10 meg gives you 2.32 millivolts. So a little bit. All right. Well, can we sense that? Yes. It's in the noise a little bit for some of the meters around here, for my scope certainly, but it's in the ballpark. Now, the last column that he lists is his ratio, which is the main current through the gold leaf times the magnetic field divided by the current through the galvanometer. And what he shows in that column is that there's a clear effect, okay? That's the point I want to make. There's something there that was seen, and that's what I'm looking to reproduce. Now, can this be reproduced? There's my artificial Hall plate, because Edwin Hall used gold leaf that was way thinner than tinfoil. My magnet out of a hard drive, and from backing out the numbers, this should be enough magnetic force. It's like it's like in the Tesla range, so it's a big number. And so I had really high hopes for my tinfoil, and I can't. I've got the scope set to 2 millivolts. I'm DC coupled. Any deflection at all I would see, assuming I could get past the noise from the switching supply. All I'm looking for is a little and nothing. I can't get anything. But when you back out the numbers, from Hall's experiment, it looks like you've got to be down in like picoamps or something. It's just ridiculous. So I don't know why I had any hope that this was going to work. Well, I used tinfoil. I used my standard switching power supply, and I used a magnet that I jacked out of a hard drive because it's a big, strong magnet. And I can tell you the answer is no. I could not see anything, and we've got some video of me going, this totally doesn't work. Now, why didn't it work? Okay, a couple of reasons I can think. Number one, I'm not using really, really thin gold leaf. I'm using tinfoil because we have lots of tinfoil. We're a little shy on gold leaf around these parts. And if you kind of imagine, right, the whole force thing, if you imagine the cross section, and this is just a random thing, if you've got a B field going this way and electrons going through that way, what I expect to happen is that the field is going to push stuff, but it's gonna move, right? It's a generalized, it's not a very focused thing. So I imagine it like particles in a cloud, sort of, kinda. And so the thicker this material is, the less constrained these charges are going to be. So do you take your reading here? Do you take it here? Do you take it here? Well, if you constrain this down to a really thin dimension, the electrons can't go very many places, and so the measurement becomes simpler, I think. Now, the other reason I can think of is that 2.32 millivolts on my very old Tektronix scope is way in the noise, and the power supply by itself is a switching supply, and it's generating all kinds of garbage that's going on that line. So I am not at all surprised that I could not see this. And it could be argued that with a little bit of gain on an op amp, you could actually pull that out of the noise. And of course, this is done as standard practice in a zillion components these days, so mine didn't work. Oh well. But I challenge you, Internet, see if you can make this work, because it would be pretty cool to see. So, Hall effect. So what? Well, measuring Hall effect just gives us a way to figure out whether or not there's a magnetic field present, right? And it's not even the only magnetic field sensing technology out there. In fact, it's about the least sensitive one that you can get. So, all of the technologies, when combined together, form a continuum of parts, all right? Of course they do. We have a lot of examples of this through our industry. But these parts, being that they're kind of coarse sensitive, they find a lot of applications in contactless sensing, in position sensing, and switching applications, right? Turns out that being able to tell that something is happening without actually touching it, that's a cool thing. We like that. And it's big business. So, you know, from the windows in your house to an assembly line at Ford, these sensors find homes in a lot of places. So the sensors are going to look like, if you go shopping for sensors, what you're going to find is that the ones that use Hall effect, the sensitivity ranges in the hundreds of Gauss, like down, like the lowest sensitivity, right? Hundreds of Gauss to, and which is tens of millitesla. And prices are generally hundreds of dollars for the really expensive ones, and these are the ones that generally say things like suitable for military and space applications in the data sheets. So this is serious stuff, man. And the little ones, you know, $1 for the cheapies and single quantities. So they're not really special necessarily, but they can be very specialized and very expensive depending on what you need them to do. If you're going to send it into space or other hostile environments, you're going to spend for it. Now, we sell exactly two. We sell the AH1815 from Diodes Incorporated. The SKU is SEN 14709, and it has a voltage input range of 2.5 to 5 volts, and it is a non-latching part. The other one is the US 1881 from Alexis. Its SKU is COM 09312, and it is 3.5 volts to 24 volts, and it's a latching part. So they're fairly different parts, but they both sell for about $1, right? I wouldn't send any of these guys into space, but you know, for $1, contactless switching, that's kind of a cool application. So what would have been really awesome is if I had used this tinfoil to heat up my pizza before actually doing the experiment. And what would have been more awesomer is if it actually worked from the tinfoil I used to heat up my pizza. But it didn't. Tinfoil is apparently not good for this. So, thank you for tuning in to Hall Effect and Lorentz Force. It was a really good time. I hope you enjoyed it. Further reading. You should definitely go, and I'll post some links for this, all of these things. You should definitely look up right-hand rule, because it's funny. You should definitely read about Lorentz Force and Hall Effect. If you just read the write-up of the experiments of Edwin Hall's, that's a lot of fun. You should definitely read about Lorentz Force, and I'm a nerd about some of this history, so I'm also going to tell you that you need to read about, like, Carl Friedrich Gauss and Oliver Heaviside and all those dudes back then that were doing this really crazy stuff. Yeah, I'll post some links and you can check it out. And I think that's all. Have we done everything? I think we've done everything. So, we'll see you next time. And I'm not even sure what the topic is going to be. But thanks for tuning in. If you have any comments, put them in the comment section below. And until next time, see ya. All right, we going? We're going! Okay. Always gotta look at my notes because I'll forget, and I always forget. Okay. I'm thinking like at some point you're gonna be like, all right, shut up. You use any of this at will. I'm just gonna spout for a moment.